preparation for sort of Thursday when I'm going to talk about the small computer. But what computers really do, more than anything, remember I've said that computers don't do amazing things, they do simple things amazingly fast, is that they mostly manipulate numbers. That's the thing that they're really good at, right? Adding, subtracting, multiplying, messing with numbers. Computers can do that really, really well. So I want to share with you today some key arithmetic circuits, okay? Circuits that do math. Now we've already done some of these. The full adder we did almost right away. As it turns out, the full adder is super important. You're going to see them over and over again today. Basically, if you can add, you can do lots of math. You can do a lot of math. So we're going to look at this circuit in detail, and this circuit will guaranteed be on the final exam, similarly to the homework that I will be showing you. So if you look on, maybe just on Moodle here, I want to point out a couple things. Here is the circuit. This file is the one I'm going over with you in class today. Download and play with it afterwards. The homework for this week is going to be the math circuits handout. That's about page 90 something or another. Paul, what is it there?
97.
97. Okay, this is page 97. And then the repeated addition multiplier is on the next page, I think, at 98. All right, and those two you should complete after today's lecture, before Thursday. Thursday we'll talk about the small computer, and then the small computer worksheet will be due on, this will all be due on Tuesday. Okay, so, I did want to just make a couple mentions about Lab 8. So Lab 8, post-lab, is due 1 week after you complete the lab. So for those of you that completed it last week and you're like, I'm done, I'm finished, then you should be turning it into Dr. Fong's office this week, okay? Now, as it turns out, I suppose we won't count it late because some people are going to be doing it late, but I encourage you, it's only going to get more stale if you wait any longer. Those of you that are doing more work, okay, and are going to be working in lab a second week in Lab 8, then you have the following week to complete it. So 1 week after you complete the lab, it is due to Dr. Fong's office box, like where you put your pre-labs. Okay. Also, you're going to be uploading a video of your files, similar to the ones that you guys watched, right? You watched a few of them to see. And a lot of your phones are just really high def and just wonderful now, but they make these huge files. Okay, Moodle doesn't like huge files, and so you may need to compress them. There's lots of ways to compress them. I'm not saying you have to do it my way, but if you don't know a good way, look at that. That gives you some suggestions. It's actually this Clip Champ is a nice video where you don't have to download any code. You just upload it, they compress it, you download it again, and it works pretty good. A few instructions on that. Now, I do only want one video uploaded, so if there's, if you have 2 or even 3 partners in your lab, one person uploads the video, the other person uploads a file named the names of the students who are partners, lab partners. That way we can go and say, okay, if it's, John and Bob here. Bob has the video, John just has a file. I'll give the same grade to both of them. Okay, but we don't need to fill up Moodle with 2 copies of these huge files. And it's less work for you guys.
So just load a blank file?
It's a text, yeah, just a text file whose name is the name of your, you don't have to put anything in it.
Okay.
Yeah, if you want to put something in it, I did my lab with this person, it's about that. That would probably be a nice thing to add, but you don't have to. Okay. But if you don't upload anything, we're going to assume it's a 0 and you won't get credit for that, which is really a bummer, so don't do that. Any questions on those logistics? All right, let's take a look at this circuit. I got to begin to share about a little bit last time. This is a beautiful circuit. It's very small. David.
Oh, do we need to turn in 2 copies of the lab report, or just the one for lab 8?
That's a good question. I'm actually, I do not know what Dr. Fong has said about that. I defer to her.
Okay.
If she has said that that you only have to turn in 1, I'm good if she said that. I'm not saying that.
Okay.
Okay, so I'll just defer, ask her that question. Okay. How far did we get last time on this? Between the 2 sections, I sometimes forget. Did I talk about this much at all?
No.
Okay, all right. Yeah, I didn't do twice. This is, well, let's take a look at it. It says at the top that it's a 2's complement adder subtractor, and that's exactly what it is. This thing will accept 2's complement numbers, and those numbers could be anywhere from, well, let's kind of go over this just as a good reminder. These numbers right here are the positive numbers, right? 0 through 7, just like we're used to. In fact, maybe I should do just a little bit of review. If I had this number, it's a nice 5-bit number, and I said that this was in a system that could handle negative numbers, what number would you tell me that is? Positive 12, right, everybody? It doesn't matter what system it is. If the most significant bit is a 0, we know it's a positive number, and the value is 12 here. Now, what if I gave you this number?
-10. If you assume previous.
Okay, say that a little louder, Hunter.
Depends on the system.
Yes, the negative numbers are all different. They have different encodings, so you can't answer this one definitively until you ask me another question, right? If I said this was sign and magnitude, you would say it's -10, right? Sign and magnitude, -10, great. If I said it was 1's complement, what would you say?
-5.
-5, right? And if it was 2's complement,
-6.
it's actually -6. Now that's the harder one to figure out. Remember, you copy all zeros till you hit the first one, then copy that one, then flip all remaining bits. Right? Or flip all bits and add 1, whichever you want to do. I like that, it's a little faster. So notice this number is either -10, -5, or -6. Now, it's not unusual that 1's complement and 2's complement are differed by just 1. But this is kind of, it's going completely the opposite direction. All bets are off on the 1's complement. Okay, so this thing is going to do it for 2's complement numbers. So the positive numbers would be 0 through 7. These guys all here would be the negatives, right? So, remember this trick? What number is this? In 2's complement now, 2's complement. -1, and this is -1, and infinite number of 1's is -1, right? Because they're really just that sign extension we talk about. Just like adding zeros to the front of a number doesn't change the number. Adding 1's to the beginning of a negative number is just saying, continuing to say I'm negative. All right. This is the largest negative number, and what is it? -8, right? I've done a little kind of cheat sheet to make it easy for you today. That cheat sheet will not be on the test. Right? You're going to have to know that. Here's what, let's just study this. If we look for complexity, there's not a lot here. There's really not a lot here. This is a full adder. All it can do is add numbers, right? Does it add negative numbers? Well, it's going to, but we didn't design it to do that, right? This is just the full adder that we designed back in lab number 2. What are these things? Those are exclusive OR gates. Let's talk about an XOR. There's going to be a question or two on the test about these, so let's pay attention here. Now, I'm going to treat this a little bit differently. Did I do this last time? You guys have this? Okay, just want to make sure. If I have a control bit and the bit of X, and I want to look at my output F here, let's consider the following. Who wants a pen that's kind of okay but not really great? You want? There you go. Get rid of these. There. One of these is brand new. So here's my new. Okay, here we go. Let's look at this. If C was equal to 0, I think about this as my control bit. What's the relationship? Well, actually, I guess we need to finish this. That's how exclusive OR works, right? It gives me an output of 1 whenever the inputs are different. Whenever they're different. Okay. Now, if I were to write this, F is equal to, see that's the same as X? It's the same as X. When C is 0, it didn't affect it. What would I write here? When C is 1? X naught. Okay, so an exclusive OR gate is commonly used as a conditional inverter. do it a lot. Field programmable gate arrays, CPLDs, lots of other places we use it this way. So if we give it a 0, it just sends it right straight through. If we give it a 1, it flips it upside down, makes it a NOT. So I want you to look at what's happening. Let me start with it in this condition. Let's start with something simple here. Let's do this. What is 1 plus 1? 2. Everything's cool with that, right? Now let's look at what these exclusive OR gates are doing here. When this is low, 0, 0, 0, 1 comes in, 0, 0, 0, 1 goes out. It's as if they're not even there. They're like transparent, right? They did this operation and they just passed X right through them. Didn't touch it. They did add 1 gate delay, which is a little bit of a bummer, but that's what we have to do here, right? Okay, let's look about this name of this command signal. What does this do when it's low? It adds. When this is high, it's going to subtract.